Welcome back to asymptotics and perturbation methods. We're continuing our work on the method of multiple scales. Today, I would like to discuss the simplest example of a multiple scale perturbation method. It's a technique known as two-timing because it involves two timescales, a fast and a slow timescale. You can certainly have problems with more than two timescales, so any number is possible. You could have three timing or four timing or whatever. But let's focus on this simplest case. And I want to do two examples in some detail. One is to finish up something we discussed in the last lecture, which was a model problem of a damped harmonic oscillator, where we saw that just using regular perturbation theory didn't work because of the presence of what we called secular terms, these terms that blow up to infinity as time goes to infinity, even though the actual solution doesn't have such terms. So we'll see how the method of two-timing resolves that problem. And then I want to apply the method to a more genuine, interesting problem, not a model problem that we can't solve explicitly. Famous nonlinear oscillator called the van der Pol oscillator. So we'll see what two-timing does for that. It's pretty nifty. All right, so let me share my screen here. All right, so as I say, it is the simplest multiple scale technique out there. So we're going to use these two time scales, t, the ordinary time that enters the problem, and then a much longer time scale, epsilon t, which we'll call tau. And in the problems that we're going to discuss, there will be oscillations occurring on the fast time scale, and their amplitude will change on this much longer time scale. So we're studying weakly nonlinear oscillators, meaning they're very close to being undamped, unforced simple harmonic oscillators that would just, left to their own, would just oscillate at a constant amplitude. But because of the presence of the weak, either weak damping or some other weak nonlinear term, the amplitude can drift on this long time scale of 1 over epsilon. And so we'll be seeing that effect in what we do. All right, so the first move in the method of two-timing is really kind of bizarre. And I can't give you good intuition for it because I don't really have it myself, even though I've been thinking about this for 30 years or so, maybe now 40 years. I still find this first step really mysterious, which is that we're going to treat t and tau as if they were independent variables. But they're not. One is directly proportional to the other. So there's something that seems wrong-headed about the method to begin with, except it works. I don't happen to know the proof that it gives asymptotic results. I've never been curious enough to look that up or think about it. I probably should. But anyway, we're going to just operate very mechanically, pretending that t and tau are independent. And you'll see that everything works very nicely, but it's an interesting theoretical issue to explain why this works as well as it does. So let me clarify what I'm talking about. So like, suppose I wanted to just, since I'm going to be doing ordinary differential equations, I'll have occasion to compute y dot time derivative with respect to t. And in the method of multiple scales, you treat it like this. Since we're thinking of t and tau as independent, we take this derivative is regarded as a total derivative, which has partial derivative contributions, partial y with respect to t, and a term that is partial y with respect to tau. And then we have to take account of the fact that tau dt gives us an epsilon contribution through this relationship. Where here, it looks like we're kind of treating them as if they depend on each other, tau and t, and we are. But after this, we won't. So with this maneuver right here, we get this way that the time derivative changes. It becomes partial y with respect to t plus epsilon partial y with respect to tau. And doing that same kind of calculation once more gives us a formula for the second derivative, which ends up giving us 3 terms. So I'm going to use subscripts for partial derivatives sometimes. I'll also use subscripts to number things in perturbation theory as like the 0th order term, the 1st order term, or whatever. So we'll be getting dual use out of our subscripts today. Anyway, so we have YTT. Then there's another term, which is this mixed derivative, YT tau, that gets a 2 epsilon in front of it when we do this operator twice. And then we get an epsilon squared term coming from doing this operation twice. So that's how derivatives transform. And so if we want, I could go to high order if I want, but throughout I'm going to neglect the order epsilon squared. We don't need them to make the points that we want to make today. There are some problems where you might want to keep them, but not today. Okay, so let me barge in with our example from last time, the weakly damped linear oscillator, which you'll remember looks like this. It's y double dot plus y equals 0. That would be undamped harmonic oscillator, plus this small damping term, 2 epsilon y dot. And the initial conditions we used were that a mass was sort of displaced by an amount that we called A. And so y0 is A, and it had no initial velocity. It was at rest. So we just pull it off to the side and then let it go. And now using this approach with the 2 timing, I can replace my second derivative with this expression that I had written above for the second derivative. And I'm just going to, as I say, neglect the order epsilon squared term. So there I'm just copying from up here. And then I do the same thing for the first derivative. I only need to keep a YT term. So just this term, because this epsilon term is itself being multiplied by an epsilon out front. So that would make order epsilon squared that we're ignoring. And finally, there's y itself coming from there. All right, so that's everything that we need. And then if we further do what looks like regular perturbation theory on y, writing it as y0 plus epsilon y1, again, ignoring the order epsilon squared, plug all of that junk into here and collect terms of different orders. So we're left with, after the substitution, this expression here. So just to stare at it, right, if I plug in this y0 plus epsilon y1 into this second derivative, I'll get a term like y0 tt at order epsilon. I also get an epsilon y1 tt. Plug this stuff into here. Anyway, you get the idea. Just going to be doing a lot of plugging in. Keep track of everything that's order epsilon or order 1, and you get this equation. So reading off the order 1 terms, there's only 2 of them, this and this. Everything else has an epsilon in front of it. So at order 1, I'm left with this equation. And at order, well, actually, while I'm there, let me just solve it. So this is a simple harmonic oscillator. Now, in problems like this, it's convenient to work with complex notation. So I'm going to use that. I mean, I could write the general solution as sines and cosines, but it's a little more convenient to use this, a e to the it plus a star e to the minus it way of solving this equation. Now here's the first part that's slightly interesting. If we were just doing an ordinary differential equation, this would be my solution where the a's would be constant. A star means complex conjugate. So A is a complex number, potentially here. These A's would be constants. But here, because these derivatives are to be understood as partial derivatives with respect to t, and I still have that independent variable tau floating around, you should really think of the A's, the A and the A star, as being functions of tau. They're functions of the slow variable tau, right? Because they would be treated as constants with respect to this partial derivative with respect to t under our assumption that the tau and t should be regarded as independent. So A has to be a function of tau, which is telling you something physically, that you're now dealing with a problem that involves a fast oscillation with a slowly varying amplitude, which we actually know is true. This was the physical intuition behind the method when it was developed, I don't know, maybe in the 50s or 60s of the last century, that these problems have slowly varying amplitude in addition to their fast oscillation. So anyway, this is coming out of the method at this point, and we don't have a formula for this slowly varying amplitude. We're going to derive an equation that will govern it, but that comes at the next order of perturbation theory, not at order 1, but at order epsilon. So as I say, the ordinary differential equation for this unknown amplitude A will pop up at the next order. And in fact, it'll be determined by the condition that we don't want any secular terms. So like we had in the Lindstedt method from last time, the condition to eliminate secular terms, that gave us a frequency correction in the Duffing equation. Here, in this more general method of multiple scales, the condition that we want to remove secular terms will give us an evolution equation for the amplitude. So it's very nice. That's in fact an advantage over Lindstedt's method. You'll remember that Lindstedt's method only gave us periodic solutions. It could not capture transient behavior. It could not capture the slow change in amplitude if there were any, whereas this method can. So anyway, going to the next order, I have to read off the order epsilon terms in this equation. And so you'll see there are 4 of them, right? I've got this one, this, and this. So those 4, hopefully I've got them all, come down at this order epsilon equation. And I've grouped things in a way that I keep this simple harmonic oscillator linear operator on the left. In other words, I'm taking a second derivative with respect to t plus the identity, hitting the function y1. That's the operator that will appear at every order of perturbation theory. Whereas on the right-hand side, you're going to get stuff that came from lower orders, which in this case, there's only y0, so we have some junk involving y0, which acts as a forcing term on the linear oscillator for y1. Okay, so there it is. Now, I use my solution for y0 that was derived above here and pop it in, take this, stuff it in there and there. And so when we do that, we get this slightly messy expression here on the bottom. So this is where it's advantageous actually to write AE to the IT plus complex conjugate. You only have to do half as much writing if you do things this way. So like here, I take the AE to the IT term, I take its T derivative and its tau derivative. That gives me an expression that looks like A sub tau, E to the IT, get this factor out in front because I have the -2, and then an I came down from differentiating the E to the IT with respect to T. So there's that term there. There's also its complex conjugate, which is getting thrown in there. And then similarly, this damping term, Y0 sub T, gives rise to this, and its complex conjugate also gets lumped in there. Okay, so now if I stare at that whole thing, notice that there's a common factor of an E to the IT here, and factoring it out times this term, which only depends on the slow variable tau, and then there's a factor -2i in both of these. You see something interesting, which is that the right-hand side has this forcing involving an E to the IT, which we know solves, is a solution to the homogeneous problem for this operator. In other words, we have a resonant forcing here, just like we had last time when we were dealing with the damped oscillator or the Duffing equation. We have a forcing term driving this harmonic oscillator at its natural frequency of 1. And that would cause resonance, that would cause a secular growth in the solution for Y1. if we allow it. But we don't want to allow it. We want to kill off these secular terms. That's the whole basis of this asymptotic method. So this is how we derive a condition on the amplitude A, that we're going to insist that this coefficient is 0. That is, I've got this equation here in the blue box. If I make that demand on the amplitude A, that will eliminate these secular terms, and then Y1 will not be growing at this order of perturbation theory. So this is called an amplitude equation because, of course, it's an equation that governs the amplitude in this slowly varying amplitude way of thinking about things. And so you'll hear people talk about amplitude equations in perturbation theory all the time. This is our first example of one. Aha, my dog has arrived. Oh. All right, he likes perturbation theory. Yes. All right, just take it easy there, Murray. Okay, so so I've got my amplitude equation, and making it be satisfied will let me remove the secularity that's occurring at this order of epsilon. Okay, so now you'll recognize this is a very simple equation for A. It corresponds to exponential damping, which is good because we're studying a damped oscillator and its amplitude is exponentially damped. So this method is recovering that. Whereas remember that regular perturbation theory didn't know that. It could not deal with the amplitude properly. So anyway, we make this condition, Y1 will then be bounded. We solve for the amplitude, its exponential decay. Notice on the long time scale of tau. It's a slow decay. We have some initial condition A of 0, e to the minus tau. That's our general solution of this. Okay, so next we have to deal with this initial condition to somehow relate it to the initial condition of our original oscillator problem that was expressed in terms of the y variable. Maybe I'll pause there because there's some kind of tedious algebra in this next step. Do you want to ask anything about the concept so far or any of the manipulations? Okay, so let me just keep going. Yeah, I mean, I realize this problem isn't the most fascinating since we know how to solve the damped linear oscillator exactly, but it's a way of calibrating the method and seeing what it's doing. Anyway, so all right, so here are our initial conditions. We said y of 0 is some constant A. And so in terms of t and tau, that means y of 0, 0 is A. And then remembering that this is itself, y is y0 plus epsilon y1, we have this condition equals A, but that's supposed to be true for all epsilon. And so this is regarded as an equation between power series. Actually, there should be a plus, an order epsilon squared stuff in here, but we're ignoring that. Anyway, so equating the like powers of epsilon on both sides, you get that y0, 0, 0 is going to be A, whereas this term has no order epsilon stuff here to match it. So that initial condition is going to be 0 at the next order, and so on if we go to higher orders. Okay, now we also had an initial condition on the velocity, which was y dot of 0 is 0. So translating that into the t tau language, that tells us that y0 sub t plus epsilon y1 t plus y0 tau plus dot 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 is 0. So again, reading off the different powers of epsilon, we get that y0 sub t at 0, 0 has to be 0 for this to match this. And since there's no epsilon stuff on this side, this term has to be 0 at time 0. Okay, so that's a fairly complicated way of writing the initial condition in this new framework, but that's the way it comes out. Okay, but fortunately, everything is pretty easy at this stage. We showed that y0 is just this exponential decay. And, well, sorry, the amplitude is exponentially decaying. y0, this is, the A function times e to the it plus its complex conjugate. So here's the e to the it. Here's the decaying amplitude A. And so now when we impose time being 0, This whole thing is supposed to be A. That tells us it's A0 times e to the 0, e to the I0. That's all just 1 plus complex conjugate. And since A is potentially a complex number, you have to really work with it in those terms. And so this, when you add a complex number plus its complex conjugate, you get 2 times the real part of that number. So we have 2 times real part of A0. And the other initial condition, which was the one on the derivative, can be shown to give us I A0 e to the minus tau plus its complex conjugate. Evaluating that at 0, 0 gives us I A0 plus its conjugate, which comes out to be minus 2 times the imaginary part of A at 0. If you're having trouble seeing how our imaginary part's coming in, think of A0 as being, you could do a little calculation off on the side if you want. A at 0 is the real part of A at 0 plus I times the imaginary part at 0. I don't want to gunk up my notes here too much, but you can plug that in anywhere that you're confused, and just remember that the conjugate of I is negative I, and everything will work out. Anyway, so where are we? So this whole expression for y0 at 0, 0, y0 sub t at 0, 0, that's supposed to come out to be 0. So that tells me the imaginary part of A is in fact 0. In other words, this A that I worried about being complex, actually it's real. But now we know that. And so, in fact, we can conclude by solving this little bit of complex algebra that A at 0 is just the initial amplitude over 2. Okay, so that was a little bit of a workout, but now that we've got that, we can plug that in to say that our 2-timing solution is just this. It's this initial amplitude, A over 2, the slow decay, e to the minus tau, the e to the IT fast oscillations, plus the complex conjugate, plus order epsilon stuff involving y1 that we don't really care about. The only reason we dealt with the y1 equation was to get the amplitude equation for A. We don't really need the y1 correction because it's bounded. And so this term is just simply small. It's just epsilon y1. And we could have it if we want to include it, but we don't really need it. So our prediction from 2-timing is that for the damped linear oscillator, the function y should behave like its initial amplitude, exponential decay on that amplitude on a slow time scale. So now restoring tau is equal to epsilon t. We're seeing A e to the minus epsilon t, slow decay times cosine of t. Oh, by the way, where's the cosine of t coming from? It's coming from the fact that e to the it plus its conjugate divided by 2 is another way of saying cosine of t. Right, that's Euler's formula for cosine of t. So that's why the 2 disappeared. This 2 is going in the denominator of the cosine when we write e to the it plus e to the minus it over 2 is cosine of t. So we're using that. All right, so at this point, well, what do we expect? This is supposed to be an asymptotic method that works as epsilon goes to 0 from the positive side. And it's supposed to be valid for times up to and including tau of order 1. In other words, it should hold for times of order 1 over epsilon. It's good on that long time scale, but not longer. You don't expect it to be valid much longer than that, but it does work up to that long time scale. So at this point, I want to show you how this looks when you do it in the computer, so you can see to what extent the method is working. So let me jump out of here and see if I can get Mathematica running. Okay, so, right, so we did this problem last time with the damped linear oscillator. We saw these secular terms. So let me just remind you what that looks like. I get this is the exact solution. It's kind of complicated looking, but it's got a bunch of epsilons all over the place in exponents and in amplitudes. So there's the exact solution. Now, what does it look like? And how does it compare to this expression right here, which is the prediction from regular perturbation theory? Recall that term has this undesirable epsilon t sitting right here in the amplitude. That's that secular term. So if I graph my old results from regular perturbation theory, we saw this last time, that the exact solution in blue, which is exponentially decaying, is decently matched by regular perturbation theory for short times of order 1, but then regular perturbation theory starts to screw up. Here I'm using an epsilon of 1/50th. So 1 over epsilon is a time scale around 50, which is occurring in here. So regular perturbation theory is okay up till around then, but then starts messing up at that time scale and starts growing when it shouldn't. Okay, so that was from last time. Now, let us compare what we get if we use our 2-timing approximation. So here I'm using e to the minus epsilon t cosine t, which is what our new theory predicts. So if I run that, you see that the two curves are on top of each other and you can't see them. You can't see any difference. Y exact and the asymptotic approximation look really close. So close that it's indistinguishable at this scale. Now, it's not exact. I mean, you can see this expression is a lot simpler than the exact result, which was back here. So the method is not perfect. It's not giving you the exact result. It's giving you an excellent approximation to the exact result. But there is a difference. And so I think the clearest way to see the difference is not numerically, but symbolically. Let me just ask it, do the series expansion on the exact solution with respect to epsilon and compare it to this asymptotic approximation, and let's see where they differ. So if I do that, then I get this interesting result, which is that the error between them is proportional to epsilon. We are making an order epsilon error. And that's because I didn't write down the order epsilon term. Remember, I didn't write down epsilon y1. I could. That would take care of this error. But so we're not surprised to see an order epsilon error, but still, this is a small error because epsilon is small and this term is bounded. So even at long time, this term does not cause us any trouble. However, there's this term, which says epsilon squared times t times sine t. So we're now producing a secular term at a super long time scale corresponding to this epsilon squared t. That becomes big when time is of order 1 over epsilon squared, which is extremely long into the future. But so what's happening here is because we've only used 2 timescales, we used t and epsilon t, we got a good approximation up to the slowest of those 2 timescales, but we did not account for the super long timescale of 1 over epsilon squared. So if we wanted to do that, we can, then we would need 3 timescales. And so you can systematically push the error out into the future by including more timescales. That's why it's called the method of multiple scales. So we could do that, but there's no great conceptual interest in doing it. I mean, there we'd really be better off just doing everything in Mathematica. There are some cases where you want that information at the very, very long time scale, but we don't need it for our illustrative purposes here. Okay, so I hope you found that instructive, and maybe I'll pause there to see if you want to ask anything about this.
So I take it that with more timescales, we treat all of the different timescale variables to be independent from each other?
That's right. Yes, exactly. So you do this useful fiction that all the timescales, even though they're all proportional to t, you pretend they're all independent. This really should set your pure mathematical selves jumping. And I hope it does. I haven't actually checked whether Bender and Orszag give a coherent explanation of how this method can possibly work. Honestly, I haven't read the book because I learned this technique other places. And so I've just been using it without inquiring as to its validity and justification. But so it's possible Bender and Orszag have a good explanation of it in chapter 11. I don't have a good explanation for you.
I was thinking maybe
I mean, it's out there. People know how to justify this rigorously. I just don't happen to be one of them. Sorry, Maria, I cut you off.
It's okay. I was thinking that maybe one of the behavior when T is very large is just so different than the behavior for small T that you can consider them independent.
You mean, yeah, sort of that might be yes. I mean, intuitively, that is sort of what's going on. That on the very long time scale, I mean, as far as the fast oscillations are concerned, something that's varying super slowly looks like a constant. This is not that crazy. This is like if I ask you, what is your height? You would, I mean, in fact, your height is a changing function of time. When you were a little baby, your height was very small. And then you got taller. And your height is evolving over the course of your lifetime. When you get very old, your height will start to shrink again, as you probably know from your grandparents, you know, that they start to get shorter. So a human height is something that varies on a time scale of tens of years, leaving aside the fact that it probably also varies every day a little bit from morning to night. But ignoring that, that's a very small correction. I mean, there's a secular trend in your height on a time scale of 10 years or even a year. And we ignore that because over the course of a day or a few hours, your height doesn't change that much. So it's sort of like that we're pretending that these super slowly varying quantities are effectively constant on the short time scale. And it works asymptotically. Okay, so let me move on to the more interesting problem of the van der Pol oscillator. Okay, so here we are. Van der Pol oscillator. So this is named after Balthasar van der Pol, who was an electrical engineer at the beginning of the 20th century. I just looked him up before class today. He studied a lot of math and physics in the Netherlands. He worked with J.J. Thomson, the discoverer of the electron in Cambridge in around like 1910, 1915 in there, 1920. He was very early pioneer in the study of radio. In those days, radio was a cutting edge technology. You know, the use of wireless communication to, like Marconi's work with telegraph communication across the Atlantic Ocean. That was a big mystery at the time. How did that really work? And it had to do something with the ionosphere, the charged particles up in the atmosphere, and, you know, radio waves bouncing off or something interacting. Anyway, I don't really know the story of this, but van der Pol was a very mathematically minded engineer who worked in the early days of radio, and nonlinear oscillator models arose in connection with a certain kind of electronic circuit that he studied that was called a triode oscillator, sort of an early forerunner of today's semiconductors and other amplifiers. They were important in the early days of radio. And so this equation that we're writing down here has physical meaning in that electrical engineering context. So you may have learned in a decent physics course that, like, if you write the equations for an RLC circuit, you know, resistor, inductor, capacitor, it looks like a simple harmonic oscillator with a mass on a spring and a dashpot providing damping. So you should sort of think of this not so much as a mechanical oscillator, as more of an electrical oscillator, where this term turns out to correspond to a nonlinear inductance. So I say nonlinear because of this y squared times y dot term. That's a nonlinear term, right? That's cubically nonlinear in y. And that makes it impossible to write down a closed form analytical solution for this. It's a genuine nonlinear oscillator that you have to analyze perturbatively or qualitatively in the phase plane using nonlinear dynamics techniques. So, so van der Pol studied this for small epsilon, and it's got very interesting behavior. So let me try to give you some intuition about how this thing behaves. First of all, this nonlinear damping, we're not used to that. We're used to this term not being there. We're used to linear damping, right? Where that term is constant. Epsilon is a constant. But here, this changes sign depending on if y is greater than or less than 1 in absolute value. So as you can see, it behaves like an ordinary kind of damping, positive damping, in other words, if the amplitude is big. If the magnitude of y is greater than 1, which if you want, think in mechanical terms. I find that easier than electrical. If you picture this as a mass bobbing back and forth on a spring, when the amplitude is large, y squared minus 1 is large, and then this has large damping, meaning that if you have a large motion, it tends to damp out to something smaller. On the other hand, if it gets too small, this term becomes negative, which means that it's negative damping, which is not a familiar concept, but that corresponds to energy being pumped in rather than being dissipated. In other words, if the amplitude gets too low, it starts pumping itself back up. And so you could sort of intuitively expect that this system will settle down to some kind of oscillation at a certain amplitude where the pumping is balancing the ordinary linear damping corresponding to this epsilon y dot. Well, I mean, this system has some character of ordinary damping as well as pumping. So when the energy dissipated around one cycle is matched by the energy pumped in on average, that will be its steady state amplitude. And so we want to understand, what is that amplitude? So if you've taken a nonlinear dynamics course, you probably learned that this system has a limit cycle in the phase plane. If you study the plane with axes y and y dot, and say solve the equation in a computer, you'll see that it spirals down onto a very nice, almost perfectly circular limit cycle. And if you start inside the limit cycle, you'll slowly spiral out onto it. And so there's some essentially circle sitting here with some amplitude centered at the origin that this system wants to approach. And our question is, how does it approach that limit cycle? Like, what's the time dependence of the approach? And what's the size of that limit cycle? What's its radius? Physically, though, this corresponds to this self-sustained oscillation. The system just oscillates on its own with some amplitude that doesn't depend on the initial conditions. As long as you don't start at the origin where the whole thing is damped out, that's an unstable point anyway. I mean, if you perturb away from that, the system just winds its way out to some oscillation, always the same oscillation from anywhere. Actually, van der Pol wrote some interesting papers in the 20s about biological oscillations. He had really wide interests, and he started thinking, well, what about like heart cells? Heart cells, or they will just oscillate at a constant amplitude themselves. They don't look like sinusoids, but still they have a self-sustained rhythm. And if you try to damp one out, it comes back and starts beating again, as long as you keep it alive. So he saw his oscillators as having a connection with self-sustained biological oscillations, which they do. And so we use van der Pol oscillators all the time in mathematical biology. Anyway, so the questions before us are, what's the approximate amplitude of this limit cycle in the small epsilon limit? And by the way, that's sort of a puzzling thing from the standpoint of linear math, because if epsilon is strictly equal to 0, if we just ignored epsilon altogether, if this term weren't here, that system is a simple harmonic oscillator, which can oscillate at any amplitude. I mean, that's a mass on a spring with no damping. You can have a big oscillation or a small oscillation, and it'll go on forever, if there were 0 damping, no friction. So the damping being absent completely means that the amplitude is undetermined, whereas somehow this system knows what amplitude to have, even for epsilon arbitrarily close to 0, as long as it's not exactly 0. So anyway, somehow one amplitude is being picked out. And that's our question. What amplitude is being picked out? The other question, then, as I said, is how do the solutions approach the limit cycle? Okay, so we're going to solve all of that. Now, I guess I haven't written this part out, so let me begin writing that in real time. I've written out a lot of it, but not all of it. Okay, so if you were going to solve this, you're just going to repeat what we did before. So we'll write y of t tau is, think of it as y of t and epsilon. I'm already messing up. Y of t, and it depends on epsilon. We'll think of it as having these two time scales. By the way, why do I think there will be two time scales? Because the damping is weak. The system basically thinks it's a simple harmonic oscillator, but it's going to slowly accumulate amplitude due to that weak pumping or weak damping term. So there is going to be an amplitude change on a long time scale. Anyway, so we do the same thing as we did before, where our y dot in this new way of thinking is capital Y sub t plus epsilon y sub tau. And the y double dot, as before, is going to be y tt plus 2 epsilon times the mixed derivative yt tau plus ... and we'll ignore the order epsilon squareds. And so then when we plug into the van der Pol equation, so we'll abbreviate that VDP for van der Pol, that translates into second derivative, so ytt plus 2 epsilon yt tau plus ... plus the weird term epsilon y squared minus 1 times y dot, where y dot now is yt plus epsilon y tau. Finally, plus y equals 0. And then we do our regular perturbation move on y by saying y is y0 plus an epsilon y1 plus ... and substitute that in to get a further monstrosity. I'm going to skip all that writing and just tell you that when you plug that in and collect terms of order 1, you get, not surprisingly, at the lowest order, y0 obeys the simple harmonic oscillator equation. And at order epsilon, the y1 term also obeys a harmonic oscillator left-hand side. So we come to expect that in perturbation theory. There's some operator that keeps appearing on the left, but then there will be terms coming from the order epsilon stuff involving y0, which end up looking like this. Minus 2 y0 t tau and minus y0 squared minus 1. It's that van der Pol term, y0 sub t. Okay. So there. Now, if we solve the order 1 equation, we'll get y0, and that's just going to give us the same thing we had last time when we did the damped oscillator. Y0 will just be something of the form a of the slow variable tau, e to the it, plus its complex conjugate. So nothing new there. Actually, it's a little bit helpful here to be more explicit about the complex conjugate. So I'm going to write that out. Y0 of tau t, well, t tau is a of tau e to the it plus a star of tau e to the minus it. The reason I'm writing it that way is because when I deal with the cubic terms, it's going to be convenient to have the a star available. I find it easier to see what's happening in the nonlinearity. So let's now go up and look at this order epsilon term, or order epsilon equation. That becomes y1 tt. So what I'm doing here is looking at this equation, and I'm going to plug in for y0 on the right-hand side. So y1 tt plus y1 equals, all right, this is going to take some fortitude, minus 2 times, I've got to do the, what? The t tau derivative of this expression. So if I do that, I will get minus 2 times I'm going to try to copy correctly, a sub tau e to the it. And here I will write complex conjugate to save some writing. I'm going to write everything that's going to end up being proportional to either e to the it, or we're going to also get from the cubic terms some e to the 3it, but I want positive integers in my exponent. I'm not going to have like negative it or negative 3it. Those will all get lumped into complex conjugates, just to have half as much writing. So anyway, I have that plus its complex. What?
When you differentiate, doesn't the minus sign go in front, so then you have minus complex conjugate?
I'm sure everything I'm saying is going to work here. Let me write the next term. When I write the cubic term, I'll write everything out, and you'll see I'm going to do what you're asking me to do about the negative sign. But I think so far what's written is okay. Let me be more explicit with the cubic, and you'll be happy about that. So with the cubic term, meaning this one, I'll write y0 squared minus 1 times y0 sub t. So let's write that out. Minus, okay, first I have to write y0 squared minus 1. So that's a squared. Let me try to write cleanly here. A squared e to the 2it plus a star squared e to the negative 2it plus, then there's a cross term from the squaring of those that gives me a 2a star, and the e to the it times the e to the minus it cancel to make a 1. And then I have to say minus 1. That's coming from this minus 1 right here. So I've just done y0 squared minus 1. And then that whole thing is times the term that Maria wants me to write out completely, which I will now write out, which is what? I have to do y0 sub t. So let's do that. That's I a e to the it, and then I'm doing plus the derivative of the complex conjugate of that. So as you said, Maria, that gives me a minus I a star e to the minus it. There, that's all good. And the reason I wrote out all that stuff is because I want to collect all the terms proportional to e to the it. Remember, those are the terms that will cause resonance. E to the it is what you have to keep your eye on. So what can possibly generate an e to the it? on the right-hand side here? Well, let me just collect everything. Y1 TT plus Y1 equals, well, first of all, there's an uninteresting term, e to the 3it times minus I a cubed. So where's that coming from? I mean, that's the result of this, a squared e to the 2it times this e to the it times ia, and there's a negative sign out front there. So there's that. That is not of any great interest because it doesn't cause resonance and it doesn't lead to secular terms, and it doesn't give us any information about how the amplitude behaves. That's what we're really after here. We're looking for the amplitude equation on A, because that's going to govern the approach to the limit cycle. So this term doesn't help us in that respect. But the term that does help us is all the stuff proportional to e to the it. So let's now calmly figure out what that is. E to the it times, so I'll just write it down and we can verify it in a minute. Minus 2i a sub tau minus I a times 2 modulus of a squared minus 1 plus I a squared a star plus complex conjugate of the whole thing that I've written so far is the right-hand side. So, all right, so let's look at this term in the big bracket. All right, how do I generate that term? Well, all right, this right here, a tau e to the it times -2, that's appearing here. That didn't come from the cubic. The cubic, though, if I try to read off, how can I get an e to the it out of the cubic? Here's one way. I could do this ia e to the it times stuff that have no e to the it, which are these two terms. And those two terms, I've used the fact that a times its conjugate is what I'm calling the modulus or the magnitude of a squared, the complex number a, its magnitude squared. So that's giving me this term, 2 magnitude of a squared minus 1. That's from here. But then what's interesting is I can also generate an e to the it by doing an e to the 2it times an e to the -it. And so that produces stuff that looks like a squared times a star times this factor of I sitting here. And then there's a negative sign times this negative sign. So that's why I have a plus I, a squared, a star. Now, a squared, a star is itself, you could use one of those a's to multiply the a star and get a modulus squared, and then leave the other a behind. So if I clean everything up, here's the point. This all, this whole thing, this is my resonant forcing. So this resonant forcing will produce secular terms, again, because of resonance of a simple harmonic oscillator, terms growing proportional to t. It will produce secular terms in Y1 unless we make it be 0, make that bracket be 0, and that is what we're going to do. So we're going to, unless that big bracket equals 0. And so that's how we avoid the secular terms. So imposing that, that gives us, after you clean it up a little bit, notice it's going to give us an amplitude equation, because you can see from here, there's an equation involving the derivative of A is being related to A and its conjugate. It's some kind of equation on A itself, an ordinary differential equation on A with respect to the slow time tau. So it's exactly what we want. And when we write it out, we get 2A sub tau equals A minus 2 magnitude of A squared times A plus A squared A star, where I'm just copying, not doing anything clever, just canceling out a bunch of i's. But then hopefully from here, you recognize these two terms can be grouped together. I mean, this is also A times magnitude of A squared. So I end up getting A minus magnitude of A squared times A. And so let me write that as a little differential equation. dA by d tau equals 1/2 A 1 minus magnitude of A all squared for the complex number A. That's the amplitude equation for this A of tau, which, as I say, is a complex number. Now, you might be wondering about the complex conjugate that we had in the whole thing up here. Right, I have this equation, which is being forced resonantly by this term with this coefficient that we've set to 0. But if you're really on your game, you might be thinking, wait a second, though. When I said complex conjugate, that means there's going to be another term that's an e to the minus it times the complex conjugate of this coefficient. And that would also cause resonant forcing. However, it's going to give you the same condition, because the complex conjugate of this whole term is just the conjugate of this times the conjugate of this. So setting this bracket to 0 takes care of both the e to the it and the e to the minus it forcing. One equation kills both secular producing forcings. Okay, so anyway, that's all we need for the amplitude equation. You want to ask anything up till this point? We have to solve this amplitude equation, but let's rest here for a minute.
So a priori, the reason that we know that we don't want these secular terms comes from like the phase plane analysis, for example.
You could say it that way. We know that this thing doesn't have any solutions that go to infinity. You can prove that all the solutions of van der Pol's equation stay bounded for all time. So yeah, you could reason it like that. Yes, I mean, if there are problems where blow up occurs physically or mathematically, then you may need secular terms. They may really be there in the representation of the solution. But here, where we have good reason to think that this character of the solution will be a slowly varying amplitude that stays bounded times a fast oscillation, we have every reason to kill the secular terms. Yeah, that's right. Okay, so I think at this point I might have reverted to writing things out. Let me see, because I wasn't sure how long all this would take. Yeah, I just never know how many pages I'm going to need, but so I have an empty page. But all right, so let's jump back into pre-written stuff. Okay, so there's my amplitude equation, and I now want to solve it. Right? I mean, realize you're solving for this A being complex. It requires a little bit of care. So a good approach is to use polar coordinates. We think that this problem is going to have a circular, approximately circular limit cycle. So that's a pretty natural move. And we think it's going to have a circular limit cycle because remember, if there were no damping at all, the trajectories in the phase plane for the harmonic oscillator are perfect circles. You can show that by conservation of energy. So we think the orbits are nearly circular. Anyway, so let me plug this in. The amplitude is going to be the complex amplitude A is a real amplitude R, think of it as a radius in the phase plane, times an e to the I theta t. So theta playing the role of a phase or an angle. E to the I theta of tau. It also varies slowly. So I do that, I take my derivative, now prime is going to mean slow time derivative with respect to tau. And differentiating this with the product rule, you get r prime e to the I theta plus ir theta prime e to the I theta. And so I'm now going to substitute into my differential equation, my amplitude equation for A. I'll substitute this expression for A prime on both sides. Well, sorry, I'm going to substitute for A prime in here, and then I'm going to substitute this A in here and there. And if you do all that, then you get this equation. Notice the convenient aspect that the magnitude of A squared is just R squared, right? Because it's the magnitude of this A is just R. E to the I theta has magnitude 1, of course. So anyway, we have that. And now if you look at this equation, well, you can look at it in terms of, let's look at this equation. You'll notice that there's some e to the I thetas everywhere. So let me cancel them out. And then you're left with a term r prime that is real, whereas this term I r theta prime is pure imaginary. And on this side, well, we only see something that's real now that we've canceled out the e to the I theta. So equating the real and imaginary parts, you get the equation for r to be r prime is a half r times 1 minus r squared. Nice little cubic differential equation that's separable for r. And theta prime is just 0. At this order of perturbation theory, the theta is not going to change on this time scale, meaning the phase of the oscillations. It's just going to oscillate like at the same e to the it, but it doesn't have any phase drift. In other words, its frequency isn't changing from 1. Remember, in the Duffing oscillator, the frequency was changing at order epsilon. Here, it's not going to. The van der Pol oscillator doesn't have a changed frequency at this order of perturbation theory. It does at the next order at epsilon squared, but we're not going to discuss that today. Anyway, so I have these equations for r prime and theta prime with respect to the slow variable. And we could analyze this qualitatively with a phase line argument. Rather than phase plane, it's a phase line because it's one-dimensional. So you can observe that if you graph r prime versus r, and the phase point is confined to the r axis, if you just draw the graph of r prime, this cubic has a positive slope at the origin, comes down, goes like that, cuts through at r equals 1. Of course, when r is 1, this is 0. And so the flow on the r axis is just monotonically towards r equals 1. And so on this long time scale, in this slow flow on the tau time scale, r is going to asymptotically approach 1. So that's a nice little conclusion. But we can see what that, actually how that occurs as a function of time, tau, by solving this equation, rather than just be qualitative about it. Okay, so I'm just making this remark here that theta stays constant on this time scale. But rather than just being quantitative, let's really solve this equation for r. Okay, so here it is. It's not bad. It's a cubic differential equation, and it's of the type that we teach in ODEs. It's called a Bernoulli equation. And you could solve it with either partial fractions after separation of variables, or you could just pop it into Mathematica or your favorite software, Maple, Sage, whatever. Or if you like doing things by hand, here's a little trick. This is a trick that works for Bernoulli equations. You can introduce a new variable that's 1 over the original variable, in this case, r, to its appropriate power. I think it's supposed to be 1 less than this exponent, 3. So if you guess u equals 1 over r squared, watch what nifty things happen. You can differentiate u to get an equation for u. So I get u prime is minus 2 over r cubed from differentiating this times a chain rule term r prime. Then I substitute for r prime using this differential equation. So r prime over r. My ODE for u becomes u prime is minus 2 times u. The r prime over r gives me a half minus a half r squared. But that's rewriting r squared as 1 over u. This becomes negative u plus 1. So I'm doing it fast, but the point is you convert the equation to something linear in u. So then you can instantly write down the answer. U of tau is 1 plus c e to the minus tau, and then back substitute to get in terms of r. So you get r to the negative 2 is 1 plus c e to the minus tau, where c is related to the initial condition for r0 by c equals r0 to the minus 2 minus 1. So putting all that together, we get this beautiful exact solution for the evolution of this amplitude r as a function of tau. There it is. It's a nice little formula. Okay, so let's go back to our original variables, y. The leading order behavior, y0, is now going to be r e to the I theta. Remember, this is my complex amplitude. So complex amplitude times e to the it plus complex conjugate is giving me r e to the I, then the t plus theta 0, because remember, theta doesn't change on this time scale. It's just theta 0. So we get this plus its complex conjugate. And all that can be rewritten in terms of cosine at the cost of introducing a factor of 2. So I have 2, right, because this sum is cosine times 2 of t plus theta. So there's my exact solution for y0. And now going back to the original time variables, we're predicting this phenomenal exact asymptotic approximation for the lowest order behavior. Y as a function of t and epsilon for the van der Pol is predicted to be 2 cosine, this fast oscillation, times this slowly varying amplitude sitting down here. And this is supposed to work as epsilon goes to 0 from the positive side on timescales up to and including times of order 1 over epsilon. So this governs the transient approach to the limit cycle. And so you can now see from this formula, if you take the t going to infinity limit, this whole term is going to disappear, and you're just going to get 2 over a square root of 1, which is 2. So we're predicting that the van der Pol has, in the original variables, an amplitude of 2. And now let me show you what the computer has to say about this. So let me jump out of here and share my desktop. All right, so that was the old problem. Don't need to save that. And here's the van der Pol by 2 timing. So just for the sake of discussion, let me pick my epsilon to be 0.1, moderately small, not super small. I'm going to start the system at some amplitude. I picked it to be a half, doesn't really matter what that is. Remember, we're thinking it's going to go to an amplitude of 2 in the long run. So let's start it at a half. I run it for 150 time units. We think that with epsilon of 0.1, the time scale for the evolution of the amplitude should be of the order of 1 over epsilon, like 10. So this will be 15 of those long time scales. that I'm running the whole thing for. So if I solve it numerically, Mathematica generates what it calls an interpolating function. I can graph it. And you see that I've got these relatively fast oscillations on a time scale of, it takes 2 pi for the period, right? Because it's cosine of t, has a period of 2 pi. So in 20 time units, it's going to have about 3 oscillations, which it does. So it's doing its fast oscillations, but notice its amplitude is gradually building up and saturating at 2, as predicted. Okay, so that's how it behaves. And I can then ask, well, Mathematica, since you're good at this, find the amplitude, r of tau, and it does for this particular choice of initial condition. It's giving me this number 15. And if I compare the amplitude predicted by 2 timing with what we just, so here's the 2 times this r of tau that I just calculated. The 2, remember, I need because that 2 appeared in my formula for y. So I graph this, and you see that the orange curve is giving me the growth of the amplitude, perfectly matching the envelope on this modulated cosine wave. So it's a magnificent thing. And if you compare the whole solution, not just the envelope, not just the amplitude, I'm sorry, I want to run this, not the comment. It's another one of these situations where you can't see the difference. The asymptotics is totally nailing what the numerics is doing, even on 15 of these long time scales. 15 times a 1 over epsilon. So it's really working very well. And we'd have to wait a super long time to start seeing some other effects coming in. And as I say, if we wanted to, we could account for those effects by putting in a 3rd time scale. But anyway, I hope I've convinced you of the power of this technique of 2 timing, even if its logical foundations, as I presented them, are pretty shaky. But it's a great method. And so next time I'll show you, remember we did a problem we called the aging spring? I think we did it with the WKB method. I want to revisit the aging spring with the method of 2 timescales and show you a little deeper insight into what's going on in that aging spring problem. Okay, all right, so that's it for today. See you later.